Welcome back, complex students. This will be our last video of the year, and it's going to be something of a whirlwind overview of series, and I'm wanting to make it to an important result called the Cauchy residue theorem, which gives us a way to calculate integrals that's pretty cool, and it also gives us a way to calculate real valued integrals of a type that we wouldn't really have been able to do with what we learned in calculus. So that'll be our exciting conclusion. Let's start this brief overview of series. The good news is that series are everything's basically the same for complex variables as it was back in, say, your calculus sequence. So an infinite series, this is just where we're attempting to add up an infinite list of complex numbers, z1, z2, z3, we're adding those up. Of course, it doesn't really make sense to add infinitely many numbers, so the idea is when you say that the series converges with a sum s, it just means that if you add up the first n of these terms in that sequence, which is called a partial sum, maybe we'll call that s sub n, if you take the limit of those partial sums and you get some sort of limit, then that's the sum of the series. So let's see an example that illustrates this. So here's the so-called geometric series that you may remember from calculus. So it turns out that this series converges, and we'll figure out what its sum is briefly. And to do that, we need to look at those partial sums. So here it's the partial sum of that series. Now, you may remember from a few different homework exercises that that particular sum, 1 plus z squared all the way up to z to the n, can be expressed as 1 minus z to the n plus 1 all divided by 1 minus z. So then, if we want to figure out if that series has a sum, we need to take the limit of that. So we take the limit as n goes to infinity of this partial sum 1 plus z squared plus dot 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 up to z to the n. Then we'd really be taking the limit as n goes to infinity of 1 minus z to the n plus 1 over 1 minus z. And then to think about that limit there, there's only one term that involves n. It's this z to the n plus 1 term here. All the rest of the terms of that fraction are just constants with respect to n. So we can consider a few different cases. We can consider the case that the modulus of z is less than 1. Well, in that case, when you take the limit as n goes to infinity of that z to the n plus 1, what you're really doing is you're taking the limit as n goes to infinity of some complex number. Maybe it's a little easier to see if you convert to exponential form. It's like r e to the I theta, and you're raising that to the n plus 1. And here r is less than 1. And then this in turn equals the limit as n goes to infinity of r to the n plus 1, and then e to the I times n plus 1 theta. But the point here is that as n goes to infinity, this r to the n plus 1 term is going to go to 0. Just a basic fact from things you know before, that if you take a number that's between 0 and 1 and you raise it to a big power, you get a number close to 0, right? So anyway, this comes out to 0. And so then that tells you that the limit of the partial sum, which we know is the same as the limit as n goes to infinity of this fraction, 1 minus z to the n plus 1 over 1 minus z, that term with the n in it went to 0, and so you're just left with 1 over 1 minus z, which is the familiar formula for the sum of a geometric series. But this is only true in this case, that the modulus of z is less than 1. And then we can look at the case modulus of z is greater than 1, and there that similar sort of arguments will show that I'm going to put it in parentheses, but z to the n plus 1 goes to infinity as n goes to infinity. The modulus of that number is going to grow large. So that tells you that the limit of the partial sum just does not exist. And also, whenever modulus of z is equal to 1, you can't have z exactly equal to 1, and it's pretty clear that if z would be the real number, z equals 1, that partial sum would go to infinity. And then if z is some other non-real number with modulus 1, you've got a point on the circle, and then if you look at that z to the n plus 1 term, it's just going to sort of bounce around the circle and never converge to any particular number. So, the partial sum does not exist here too. And so the conclusion is that the series z to the n converges with some 1 over 1 minus z when the modulus of z is less than 1, and then that series just does not converge for other values of z. And it's cool that this is exactly the same formula that you get from back in calculus. This first result here just tells us that when you take your complex number z sub n, that those numbers that you're adding up, and you break them into real and imaginary components, then basically to evaluate the series of the zn's, you can break it into evaluating the separate series of the real components and the imaginary components. So what this does is it allows you to carry over results from calculus class, things like the ratio test and the root test and nth term divergence test, all those little facts you learned about convergence of series and how to determine what they converge to, and things about how to tell if the error is going to 0. All that stuff you learned, you can apply it to complex series. You just have to break it up into the real and imaginary components. And so, using this theorem, which I'm not going to prove. In fact, today I'm not going to prove anything because I'm just interested in giving a large overview. But using that theorem, you could easily establish things like corollary 1 here. It says that if you have a convergent series, then the terms that you're adding up have to tend to 0 as n goes to infinity. In other words, this. And back in calculus class, we gave a name to this. It's called the nth term divergence test. Why is it called a test for divergence? Because you can look at the contrapositive of this. If the limit of z sub n does not equal to 0, that implies that the series diverges. So it's a quick and easy check. If something diverges, you can sometimes pick up on it pretty quickly just by looking at the nth term that you're adding and take the limit of it and see if it goes to 0. And a second corollary is something that you would have seen in calculus class. It just says that if you take the modulus of the terms and add them up and that converges, in other words, if the series converges absolutely, then the original series has to converge. So what I have here in blue, so absolute convergence implies convergence. And then there's, the standard results about linearity would hold true for series with complex numbers, just like they did back in calculus class. So if you multiply a series times a constant, you can pull the constant into the series, or vice versa. And if you're adding two convergent series, you can combine that into one series by adding the terms. And we also have, convergence of series are unique. All of these things you can prove. We're not going to. So next, we want to talk about Taylor series. Taylor series give you a way to represent analytic functions with a series, which is pretty useful because that takes some strange function like a natural log or trig function or whatever and converts it into sort of ordinary arithmetic of sums and products. So the result here is that if your function is analytic on a disk centered at z0 of radius r0, so we have analyticity on some disk, then the function f of z here that's analytic has a power series representation. So in other words, you can write f of z equals to a series, and the coefficients of that series are given by this formula here. And of course, that's the familiar formula for the coefficients of a Taylor series. And so what we're talking about here is a Taylor series, right? So the series you get from this theorem is called the Taylor series of f at z0. So we chose a point. We have to have a point, where that's the center of a disk where the function is analytic to make sense of this. And anyway, the function converges, or that series converges to that function value for each point in that disk. So it gives you a different way to think about your function. It basically takes the function and breaks it up as into ordinary arithmetic, like I said earlier, which is very useful. Let's do an example here where we find the Taylor series of, f of z equals e to the z with the center point z equals 0. By the way, you may remember whenever you do a Taylor series centered at 0, people often use the term Maclaurin series for that. I'm just going to call them Taylor series in general, though. I don't like having to bother with that Maclaurin term. In any event, let's do this. So in order to do a Taylor series, basically it just comes down to you got to calculate those coefficients that have that formula, the nth derivative at z naught divided by n factorial. So for f of z equals e to the z, this is particularly easy because if f of z is equal to e to the z, then we know that any derivative of that exponential function is also equal to e to the z. And then we can plug 0 into all those, and we get e to the 0, which is 1. And this is true for all n equal to 0, 1, 2, so on and so forth. Then we know that the nth coefficient, a sub n, is going to be, well, the formula for it is the nth derivative at 0 over n factorial. So that's just going to be 1 over n factorial here. And so our Taylor series for f of z equals e to the z is the sum n equals 0 to infinity. And then our a sub n's are 1 over n factorial, and then times z to the n. Or in more compact form here, just z to the n over n factorial. Now, the hypotheses for that theorem said if your function is analytic on a certain size disk centered at the point, then you have convergence to the function of the series on that whole disk. Well, our particular function here is entire, so you can think, the r naught in the theorem above equals infinity. So the radius of convergence of this series is infinite. So that means that the Taylor series represents the function on the entire complex plane. So what we know is that e to the z is equal to this series, n equals 0 to infinity, z to the n over n factorial, for all z whose modulus is less than infinity. In other words, any complex number. This is nice. We have a series representation for a pretty important function, e to the z. And you can do the same process for several of our most common types of functions and get Taylor series representations for them. And so here's a little sort of summary of some common ones. The first one there is the geometric series that I worked out a little earlier. Now, when I worked that out a little earlier, it wasn't as a Taylor series, but it turns out that you can do the Taylor series for that function 1 over 1 minus z, and you get the same answer and the same interval or same radius of convergence. And then we did e to the z there, and you can see the series representations for sine of z, cosine of z. You may recognize those that's the same formulas that you had back in calculus. And there's a couple of other ones there for hyperbolic sine and hyperbolic cosine that sort of mirror the formulas for regular old sine and cosine, just without the alternating signs. And those are all pretty easy to derivate from the theorem on Taylor series. And what's more is you can use them and sort of manipulate them in sort of standard ways to get series for other kinds of functions, which is pretty useful, as we'll see. So for example, I'd like to take this function z over z squared plus 4 and come up with a series representation for it. So the sort of techniques that we'll do here are exactly like what you might have done back in your calculus class. Of the series representations that I have above, that one seems most related to the one for 1 over 1 minus z. So I think I'll try to manipulate it so that it looks like that series. So if we take z over z squared plus 4, let's see, I'd like there to be a 1 in the numerator, so I'm going to pull off a z. And also I'm going to factor out a 4 into the denominator, so I'll have a constant term of 1 in the bottom of that fraction. So if I pull that off, then the fraction I'm left with is 1 over, and I'll have 1 plus z squared over 4. And that second fraction there is starting to look more similar to the one for the geometric series. And if I just write it like this, it'll be in the perfect form. Write it as 1 over 1 minus negative z squared over 4. So the idea is I'm going to put z squared over 4 in place of z in the geometric series. So this would be z over 4 times the sum n equals 0 to infinity of z to the n, but now our z, instead of just being regular old z, is this term, the negative z squared over 4. So it's negative z squared over 4 to the n. And I probably want to simplify this just a little bit. So I'd have an alternating term here, negative 1 to the n, and then I'll have z to the 2n all over 4 to the n. And then I can actually pull that z over 4 inside the series, and then it would have z to the 2n plus 1 over 4 to the n plus 1. So there would be a series for that original function. We need to think about what the radius of convergence is, but we know that this works for whenever the term in yellow there has modulus less than 1. And then you can manipulate that inequality to see that we'll have mod z less than 2 for this convergence. And this is sort of a fun topic to get into, of taking sort of standard series representations of functions and then using them to get series representations of related functions. And you can take it a bit further by doing things with differentiation and integration of series that we're not going to get into here. The good news is that whatever you learned in calculus, the same techniques are going to apply here. So we're not going to spend a whole lot of time going over that, but I just want to make you aware that really there's no boogeyman hiding in the complex numbers when it comes to series. It's all the same stuff. Okay, so now we want to talk about Laurent series. So when a function is not analytic at that center point z0, we can sometimes represent that function as a series involving positive and negative powers of that z minus z0 to the nth power here. And when you do that, the resulting series is called a Laurent series. So here's the theorem that we're going to use. And it looks a bit scary. It's a little bit of a wordy theorem. Just think we're doing Taylor series, but with a little extra boost. So in this setup, we have a function that's analytic through an annular domain with an inner radius of R1 and an outer radius of R2. So in my picture at the bottom here, the place where your function is analytic is that yellow region that's it's outside of an inner circle, but inside of an outer circle, where the radiuses are R1 and R2 there. So that's where your function is analytic. And then C is just any positively oriented curve that goes around inside that annulus. A positively oriented closed contour there. Simple also, so no self-crossings on that curve. Then, here's the big point. At each point in that yellow region down there, the function f of z can be represented by the sum of two series. The first one just looks like a regular old power series, and then the second part's where you have the negative coefficients or the negative powers of z minus z naught. So we get the sort of parts where the z minus z naught's in the denominator here. And the coefficients can be given by these two formulas. So on the positive exponent part, you've got the formula a in there. So it's the kind of formula to which the extended Cauchy integral formula applies. So it looks like that sort of thing. And the b sub n's are sort of a variation on that. But the point is there's a way to calculate these coefficients. And in fact, it turns out that the a sub n's, if you happen to know that the function f there in the numerator is analytic all the way down to the center point, so analytic on the disk of radius r2, then those a sub n's you can actually compute them using the Cauchy integral formula, and it works out to be exactly the coefficients that you get for the Taylor series. You get the nth derivative evaluated at z naught divided by n factorial. It's exactly what those a sub n's work out in that special case whenever you have f as analytic all the way down to the center of that picture there on the bottom left. The good news is, though, that we will rarely ever actually compute these integrals, compute these coefficients doing integrals. In fact, it's going to go quite the other way. We're going to be able to obtain these Laurent series just by manipulation of known series. And then, because we know what the series is, it tells us what those integrals values are equal to. So finding a Laurent series is tantamount to finding a bunch of integrals. And in particular, there's one coefficient that plays a central role in sort of calculation of integrals. It's the first coefficient of the negative part of the series, the part in blue. So the coefficient b sub 1, which is just the integral 1 over 2 pi I, 1 over 2 pi I times the integral round c of f of z dz. That's what that formula devolves to when you put in n equals 1 for b sub 1 there. So that coefficient is called the residue of f at z naught, and we have this special notation at the bottom here for the residue. So the first coefficient of the negative part of the Laurent series is very special, and we give it a special name, the residue. To give you a little taste of how we find these Laurent series, let's do this example here. So it's just a rational function, 1 over z multiplied times 1 plus z squared in the denominator. And you can look at that and really quickly tell it has singularities at 0 and plus and minus I. In other words, singularities are those isolated places that cause the function be undefined and be not be analytic at a point. But this function is analytic everywhere except for at those isolated points. So in particular, it's analytic on the set where the modulus of z is between 0 and 1. So that Laurent's theorem applies to this function for those values of z with modulus between 0 and 1. And so we want to find that Laurent expansion is our goal here. So instead of doing all those integrals to get those coefficients, what I'm going to do is do 1 over z times 1 plus z squared. I can write that as 1 over z times 1 over 1 plus z squared. And that second fraction there, I'm going to use what I know about the geometric series to find a series for it. So this equals 1 over z times, just for emphasis, let's write that as 1 minus negative z squared. And then that equals, using what I know about the geometric series, it's the series n equals 0 to infinity of negative z squared to the n, which I can write as 1 over z, some negative 1 to the n, z to the 2n. And this is true whenever modulus of z, negative z squared, is less than 1. But we also know that z can't be 0 because of that fraction 1 over z. And so this is true just when mod z is between 0 and 1. So here's where we're at. So the original fraction is equal to 1 over z, and then I'm going to expand out that series that starts at 0 there. So the first term is going to be just 1. Then you'll have minus z squared, then plus z to the 4th, minus z to the 6th, and so on. And then if I go ahead and distribute that 1 over z, it becomes 1 over z minus z plus z cubed plus z to the 5th, or minus z to the 5th, plus yada yada. And so you can think of this as two separate pieces. There's this part plus this part. So this would be the Laurent expansion at z equals 0. And then, you know, the part of the Laurent expansion with negative powers of z is finite. Most of those coefficients, the b sub n's, are equal to 0. So this often happens when we're looking at like rational functions. Now I want to point out what the residue is. So the residue of f of z at z equals 0 is the b sub 1 coefficient, i.e. the coefficient of the z to the negative 1 term. So residue at z equals 0, because that's where we're centering our series of f of z, is equal to that coefficient of 1 over z, which is just 1. So you look at the 1 over z term, the coefficient there is 1. These residues are going to be central to what I want to do in the remainder of this lecture, because it turns out they can be used to calculate integrals. So by the way, I mean, just notice, like, the formula for b sub 1 is, if you go back to the previous page here, b sub 1 is that integral at the bottom here, 1 over 2 pi I integral around c of f of z dz. So this tells us that the integral around c of f of z dz would just equal 2 pi I for any c, you know, simple, positively oriented, closed, inside the domain where modulus of z is between 0 and 1, because that's where all this, you know, that's where we got our Laurent expansion working, right? So by finding that residue, we just calculated an integral, but we didn't actually do any integrals in that computation. We just took a known power series representation and manipulated it, and then that coefficient of the z to the negative 1 term popped out, and that turns out to be an integral. So this sort of captures the spirit of how we're going to be doing, you know, calculating some integrals just by finding these residues. So let's seize upon this idea of using residues to compute integrals to do the following integral. We're going to integrate e to the z minus 1 over z to the 4 round c, where c is just the unit circle, positively oriented. Let's look at e to the z minus 1 over z to the 4th, and let's find a Laurent expansion for it and make note for what values of z this thing would be true. Okay, so I'm going to write that as 1 over z to the 4th times e to the z minus 1. Now e to the z, we have a power series representation for. E to the z can be represented as 1 plus z squared over 2 factorial plus z cubed over 3 factorial, z to the 4th over 4 factorial, and so on, right? Then there's still that minus 1 there. And we can cancel off those negative 1s, and we got 1 over z to the 4th times z plus z squared over 2 factorial, and so on. And now let's distribute that z to the 4th, and I'll get 1 over z cubed plus 1 over 2 factorial times z squared plus 1 over 3 factorial times z, and then there'll be a 1 over 4 factorial, and then the next one would be z over 5 factorial plus z squared over 6 factorial. Of course, now we can see our Laurent expansion. Here's the negative exponent part of it in yellow, and then over here's the positive exponent part. Now, for what values of z is this true? The series for e to the z worked for, so this part worked for absolute z just less than infinity. So the only thing we have to watch out for is z can't be equal to 0. So this is just for any non-zero z, essentially, right? Okay, so this is the set on which we have our Laurent expansion, just the whole plane minus the origin. And we've got this simple closed curve that stays inside that region. And so we know by that theorem that the residue at z equals 0 of our original function, which was e to the z minus 1 over z to the 4th, equals that coefficient of the z to the negative 1 term. So that would be this coefficient right here. So 1 over 3 factorial. But we also know that the residue is 1 over 2 pi I integral around c of that function e to the z minus 1 over z to the 4th dz. So this bit of it right here tells us that the integral around c of e to the z minus 1 over z to the 4th dz is 2 pi I over 3 factorial, or 3 factorial 6, so this is 2 over 6 1/3, so this is pi I over 3. It's pretty nifty, huh? This brings us to Cauchy's residue theorem. This is a pretty amazing theorem. We have a curve C that's a simple closed contour, of course with positive orientation, and you have a function f that's analytic inside and on that contour, except for at a finite number of singular points, these z sub k's in this theorem, that occur inside of C. So this term singular points just means these are just places where the function's not analytic, but it is analytic all around those points. So basically our function, what's going on here is our function's analytic except for these finite number of points that are called singular points. Now, if that's the case, then you can do the integral around f, or you can do the integral around c of f using this formula. It's 2 pi I times the sum of the residues at each of those in singularities. So if we can find those residues by maybe doing some manipulation with series, then we get the integral. So it's very similar to what we were just previously doing, except for in the previous example there was just one singularity that we were integrating around, and so we didn't have to think about it so much as summing some things up. But if you have, the idea is that if your curve is going around a bunch of these singularities, then you can just do the residue at each of those places. So that means finding a series expansion centered at each of those singularities and then using that to get the residue. Let me give you an example. So we want to do this integral of 4z minus 5 all over z times z minus 1, and we're going to integrate that around the radius 2 circle centered at the origin with positive orientation. And you quickly, that function's a rational function, and we can see that the singularities, the isolated places where it's not differentiable, are at 0 and 1. Those are the two values that make it equal to 0 in the denominator. And so the game plan here is at 0 and at 1, we want to calculate those residues. Let's get the residue. Let's start at z equals 0. So to get the residue, we just have to do this Laurent. Find the Laurent expansion and then pull off the coefficient of the z to the negative 1 term. Well, 4z minus 5 over z times z minus 1. Well, let's see. How can we manipulate this? Well, we could take the 4z minus 5 part and put that over z, and then we'd have 1 over z minus 1, and that 1 over z minus 1 reminds me of the geometric series, so I'm going to manipulate that part of it so that it looks like exactly like a geometric series sum. So I'd want to write it as negative 1 over 1 minus z. And then that first fraction, I'll write it as 4 minus 5 over z, and then the next fraction is just the negative of the regular old geometric series. So That's negative 1 minus z squared minus z cubed, so on and so forth, right? And that's true when mod z is less than 1. Of course, we have to have mod z is greater than 0. Point is here, we can multiply all this out, but just at a glance, you can tell there's only going to be one term in the Laurent series that has the negative exponent on z. So it's going to look like negative 5 over z plus, and then basically you're going to have a series with positive powers of z here, which I don't care about because I'm interested in doing the residue, so I didn't want to bother trying to multiply that out and figure out how it should look. But in any event, we see here that our residue at z equals 0 of our function is negative 5. And next, let's find the residue at z equals 1. So this means we need to find the Laurent expansion centered at 1. So that means that, all of our, we're going to have to look at these sort of z minus 1 to the n sort of powers. And so what we want to do is manipulate the function so that we get a geometric series with a z minus 1 in the place where z is. So the way you can do that is just to go, well, 4z minus 5 over z times z minus 1. This time it might be easier to take the 4z minus 5 over z minus 1 and sort of leave that bit of it alone by and large. We can take that first fraction just to get a fraction with z minus 1 in the denominator sort of by itself. We could write that as 4 minus 1 over z minus 1. And you can get that breakdown by doing a little polynomial division or just by sort of playing around with it. And then that second fraction, I can write that as 1 over 1 minus z minus 1, like that. And then carrying on over here on the left, this is 4 minus 1 over z minus 1 times, and then that second fraction, I can do, I can view that as a geometric series sum, and it would be 1 plus z minus 1 plus z minus 1 squared plus z minus 1 cubed, and so on and so forth. And this is going to work whenever mod z minus 1 is less than 1. So that just means the circle centered at 1 of radius 1, that disk of radius 1, the open disk, works on that disk. And so then we can get the residue at z1 using this expansion. And so if you were to multiply all that series stuff out there, what you're going to see is that you're going to have minus 1 over z minus 1 will sort of be the term with the lowest power. And then plus, then you're going to get a series with positive powers. Well, I shouldn't say positive. Maybe I should say non-negative. There will be a constant term, non-negative powers of z minus 1. But I don't care about that part to see my residue. I can see my residue setting right there, right now. So my residue at z equals 1 of this function is equal to negative 1. So now we can apply the theorem at the top. We've got the residues, so we just have to add up the residues and multiply by 2 pi I. So what were our residues? We had negative 5 and negative 1. No, wait, it should have been a positive 5. What did I do wrong here? Oh, yeah. When I was doing my first residue here, when I distributed the negative 5z onto the negative 1, it should have been a positive 5z. So that actually is that first residue should have been a positive 5. Okay, so we got this residue, and I got this residue. So we just have to add those up and multiply by 2 pi I. So the integral around c of 4z minus 5 over z times z minus 1 dz equals 2 pi I times the sum of those two residues, so 5 plus negative 1. So that would be 8 pi I. And that's really pretty cool, I think. Whenever I teach series to calculus students, I always emphasize that series are like the DNA of a function. And just like with living things, you can decipher so much about the living thing's properties by looking at the DNA. Same thing's true with functions. You extract so much information from looking at their series representations. And so it seems kind of magical that you get this integral just by looking at certain coefficients in these series expansions, but it's a common theme with series. You deduce a lot of information from the series of a function. Here's a little theorem that comes out of the chapter on residues, which is especially nice for calculating residues of rational functions. It just tells you how to get these residues without having to do too much work. So the setup is you have two functions that are the numerator and the denominator of a fraction, and they're both analytic at some point z0. And the numerator function p is not equal to 0 at z0, but the denominator function is 0 at that point. So this is typically what we're looking at when we got a rational function and we're looking at what's going on with the singularities. In other words, the places where the denominator is equal to 0. And then we also need that the derivative evaluated at that z0 is not equal to 0. So when you take the denominator and compute its derivative at the point in question, you don't want to get 0. Then it turns out that z0 is a so-called simple pole, and the residue has this formula right here, which is, I think you'll agree that that's pretty easy to compute, especially if p and q are polynomials. To get the residue, I just have to do the value of the numerator at z0 and then divide by the value of the derivative of the denominator at z0. So it couldn't be easier. So let's apply this theorem to get the residues of this particular function here. F of z equals 1 divided by z to the 6th plus 1. Okay. Now, because the denominator is z to the 6th plus 1, we can see that the zeros of z to the 6th plus 1 are just the 6th roots of 1. And I don't want to have to consider all of them. Let's consider, let's say c sub 1 equals, we know that the zeros, right? Like, we know that these 6th roots of 1 are going to be at these points on a hexagon here. I'm just going to do these ones on the top half, here, here, and here. So this is e to the I pi over 6 is one of the 6th roots of I should say negative 1. 6th roots of negative 1. And then I, and then e to the 5i pi over 6. Those are the 6th roots of negative 1 above the real axis. So those are the ones I want to consider here. So c1 equals e to the I pi over 6. c2 equals e to the I pi over 2, which is equal to I. And c3 is e to the 5i pi over 6. I want to get the residues at each of those 3 points. Okay, so first of all, in our setup here, we have p of z is just the function 1, and q of z, the denominator function, is z to the 6th plus 1. And then you can check. We see that p of c1, p of c2, and p of c3, which are all equal to 1 because it's a constant function. None of those are equal to 0 per the setup in the theorem. So we need the p of z naught's not equal to 0. And we see that q of c1, q of c2, and q of c3 are all equal to 0. And you can also check that if you take the derivative of q, which would be 6 times z to the 5th, none of those are equal to 0. So you can check all that. I'm just stating it as a fact, but it's pretty quick computation. Calculate the derivative, plug in those points, and see that you don't got 0. Okay, so now we can get these residues. So the residue at z equals c1 of our function, 1 over z to the 6th plus 1, is p of c1 over q prime of c1. Okay, p of c1 is just 1, and q prime of c1 would be, well, q prime is 6 times z to the 5th, so this would be 6 times c1 to the 5th. So that'd be 1 over 6 times e to the I times 5 pi over 6. And if we just multiply this by e to the I pi over 6 over e to the I pi over 6, then in the denominator you would get e to the just I pi, which is negative 1. So this would be negative 1/6 times e to the I pi over 6. That'd be an easier way to look at that. Then we can do the residue at z equals c1. So that's p of c2. I'm sorry, we're doing at c2 here. P of c2 over q prime of c2. So that'd be 1 over 6 times c2 to the 5th. And what do we get here? 1/6. Okay, c2, remember, is really just I, so this is I to the 5th. So I to the 5th is just negative I. And remember, 1 over I is negative I, so this would just be the same thing as I over 6. And then the last residue at z equals c3. So that's 1 over 6 times c3 to the 5th. So that's 1 over 6 e to the, okay, so c3, remember, is e to the 5 pi over 6. So if you multiply that times 5, you get 25 I pi over 6. And I think you could just multiply this by e to the 5 pi I over 6. And in the denominator there, you get e to the 30 I pi over 6. So in other words, 5 I pi over 6. I'm sorry, it'll just be e to the 5 pi I. E to the 5 pi I is just negative 1. So this is just negative 6 down here. Okay, so there's our 3 residues at these 3 different zeros of z to the 6 plus 1. So, you know, with the theorem, armed with a theorem like this, you can calculate residues in pretty rapid fire. And, you know, I didn't even have to calculate the Laurent expansion here. This magical theorem just hands them to me just by being able to compute a derivative. So that's pretty spectacular. It's a pretty specialized theorem, mind you, but when it works great. All right, so what we want to do now is take what we learned about how to calculate these residues and apply it to an interesting situation where we can actually calculate real valued integrals using the theory of the complex variables that we've learned. In particular, what we're going to do here is look at improper integrals of these 2 forms, integral negative infinity to positive infinity, or sometimes we might want to do just 0 to infinity. So these are called improper integrals, and you may remember them back from when you were doing calculus. I think you might run into this maybe in calculus 2, or maybe calculus 3, I'm not sure. But in any event, we're talking about real valued functions here. So the sort of stuff you would have done back in calculus. We're going to leverage what we've learned about complex variables to do these kind of integrals, which is a really cool application. So just a little reminder here, these 3 bullet points. So what you learned back in calculus is that the integral from 0 to infinity of f of x, you calculate that as a limit here. So you can't really plug in, you know, infinity as an upper limit of integration. But the idea is that you replace infinity with r, some finite value, then maybe you can do that integral by using antiderivatives or something, and then you evaluate it in terms of that antiderivative using the variable r, then you let r go to infinity. And when you want to do negative infinity to positive infinity back in calculus, you had to break that up as a product of 2, or a sum of 2 improper integrals, essentially. You would do it like this. So this is how the negative infinity to positive infinity integral is defined. You sort of break it up as one that goes from negative infinity to 0, and then one that goes from 0 to positive infinity. And there's another kind of integral that you probably didn't do. You probably didn't calculate an integral from negative infinity to positive infinity this way, but this is called Cauchy's principal value of the integral, here in this pinkish color. In fact, you would have been warned back in calculus class to not calculate the integral this way, because the one in pink doesn't necessarily give the same answer as the one in green, and the one in green is sort of the standard answer. But in some special situations, you can use the one in pink to help you, and that's what we're going to be doing coming up here. So the little note in red on the side here says that if that limit in pink exists, and you know that the function f of x is even, which just means that f of negative x is the same as f of x. So it just means it has symmetry about the y-axis. If you know those 2 things, that the one in pink there, that limit exists, and you know the function is even, then the standard integral from negative infinity to positive infinity is the same as this one in pink, and also the one in blue there, the integral from 0 to infinity, is the same as half of the one in pink. So in this one special situation, when the function is even, then we can use the one in pink down there to calculate the one in blue and the one in green. And in terms of complex variables, the one in pink is the one that's easier to compute for us. That's going to be our trick moving forward. So let me talk about this sort of general method for calculating some special improper integrals. So the setup here is that our function f of x is a rational function, p of x over q of x, and it's even. So it's an even rational function, and we're talking about a function with real coefficients, so this would be an integral we could do back in calculus class. And also we want to assume that that fraction is reduced, so p and q don't have any common factors that we can cancel off, okay? So these are the kind of functions we're going to try to integrate from negative infinity to positive infinity, or from 0 to infinity. And also, we want to assume that q of x has no real zeros, but has at least 1 0 above the real axis. So even though the polynomial q of x has real coefficients, when you start looking at the zeros of it, it might have some imaginary or complex zeros, right? So we want to assume about this function q that none of its zeros are on the real axis. And it has at least one zero above the real axis, okay? So that's our setup. So here's how the method goes. First of all, we're going to name those distinct zeros of Q that lie above the real axis, Z1, Z2, up to Zn, okay? So we don't care about the zeros of Q that lie below the real axis. We're only using the ones that come above the real axis. And then step 2 is we're going to form a special contour that will be formed from the sort of positively oriented top half of the circle of radius r centered at the origin. So in the picture below, I'm calling the red part C sub r. So that's just the top half of a circle centered at the origin, radius r. And then the curve goes along the real axis from negative r to positive r. So if you follow all the way around, it forms a closed loop. If you take the red curve and the green curve in the picture at the bottom, that forms a simple closed contour. And if you choose your r sufficiently large, that curve will enclose all of the distinct zeros of Q that lie above the real axis. And you can see why we didn't want any of those zeros to be on the x-axis, because that green part would go through those zeros. So anyway, this is the gist of it. So taking those two arcs together forms the curve that we're calling C. Okay, so C is the whole closed arc. Okay, now we know from Cauchy's residue theorem, step 3 here, that the integral taken around that whole arc that encloses those blue singularities, we can use Cauchy's residue theorem to say, well, the integral around that arc of f of z would be 2 pi I times the sum of the residues here. But we also know that contour integral, we can break it up as integrating from negative r to positive r and then going around the arc c sub r. So it's just breaking that arc up into the sum of two subarcs. So if you look at in step 3 here, we have the integral around the integral around c of f equals one thing, and then the integral of f around c equals another thing. Then those two things are equal. So I can equate the integral from negative r to positive r. Notice that I could put f of x inside that integral, because if you're doing it along negative r to positive r, that arc lies on the real axis. So we're really just talking about a real integral at that point. Plus the integral of the red part has to equal 2 pi I times the sum of the residues. So you can solve for the integral in green here is what we're interested in, right? So you can solve for it in that previous equation. And so you get what we have here in step 4, that real integral from negative r to positive, should be a positive r at the top there. Anyway, the integral from negative r to positive r of f of x is the sum, 2 pi I times the sum of the residues minus the integral around the red part. So what we hope to do then is argue that the limit as r goes to infinity of the red part goes to 0, because if that happens, when you take the equation just above and take the limit as r goes to infinity, well, we get the integral from negative infinity to f of x, the improper integral, equals the sum of the residues, and then the part in red went to 0, so you just get this. So this is sort of the upshot of all that we've done in this method. We can get these two improper integrals either from negative infinity to positive infinity or from 0 to infinity just by summing up the residues and either multiplying by 2 pi I if we want to get the integral from negative infinity to positive infinity, or just multiplying by pi I if we're doing from 0 to infinity. So half of the previous result. So this really captures it right here in the green box. Calculating some regular old real-valued integrals comes down to summing up some residues and then multiplying by the appropriate multiple of pi. It's pretty cool. All right, in this example, we're just going to do the integral from 0 to infinity of the fraction 1 over x squared plus 1 dx. We might as well go ahead and do the integral from negative infinity to positive infinity while we're at it, because once you get one, you get the other just by taking half, right? Or multiplying by 2, whichever one you want to do. In fact, I think I'll start by doing this one, and then we'll just divide whatever answer we get by 2 to get the first integral. First of all, I want you to notice that the function that we're dealing with here, let's let f of x equal 1 over x to the 6th plus 1. F has real coefficients. F is even. If you do f of negative x, it's the same as f of x because of the even power on the x there. And f is reduced, so the numerator and denominator have no common factors. So this is the setup that we need so that, if we go back to the beginning of that method, We needed an even rational function with real coefficients that's reduced. We also need that the denominator has no real zeros and has at least one zero above the x-axis. Okay. Also, the denominator has no real zeros because, if you would set the denominator equal to 0, you get x to the 6th equals -1. Well, there are no real numbers that you raise to the 6th power and you get -1. In fact, this is the same example we were working a little earlier up here on the upper right are the zeros of z to the 6th plus 1, right? So it's e to the I pi over 6, e to the 2 pi, or e to the, they're separated by multiples, they're separated by angles of pi over 3, so this is e to the I pi over 2, e to the 5 I pi over 6. And in this, so none of the zeros fall on the real axis, and we do have some zeros above the real axis. Let's call them C1 equals e to the I pi over 6, C2 equals e to the I pi over 2, which is just I, and C3 is e to the 5 I pi over 6. So we have these three zeros for the denominator that happen above the real axis. So given this setup, if we do negative r to positive r, so next let's let c sub r be the top half of modulus z equals r of course being bigger than 0 here. In fact, let's make r bigger than 1 because that'll be big enough to enclose those zeros that we have up there, and of course positively oriented, and we'll let c be the simple closed contour depicted below. Okay, so c is that arc that consists of that red semicircle and then the green part of the x-axis there. And then we have our zeros are in here like so. E to the I pi over 6, e to the I pi over 2, e to the 5 I pi over 6 here. We know that from what we talked about earlier, integral from negative r to positive r, f of x dx, so the real valued integral, we can write that as the sum, 2 pi I times the sum of the residues. In this case, that'll be k equals 1 to 3 of the residues at z equals c sub k of f of z. So C1, C2, and C3, the ones that we have mentioned above, because those are the zeros above the x-axis. Then there's plus, then you got this integral around c sub r, the red part, of f of z dz. And so what we want to do is take the limit. So if we want to do the integral from negative infinity to positive infinity, the previous discussion that we talked about says this will be the limit as r goes to infinity of all this stuff over here. And since that sum of the residues is a constant, we can just write this like this. The limit just goes on to the integral around the curve CR. So the idea is we want to show that this limit here is equal to 0. And then all we got to do is just add up those residues and we got it made. So the integral around f of z, if we look at the modulus of this integral around c sub r of f of z dz, so that's integral around c sub r of 1 over z to the 6th plus 1 dz. Well, we're going to use that theorem that says this is less than or equal to m times the length of the curve, where m is an upper bound on the function. Well, that function, just down here to the side somewhere, 1 over z to the 6th plus 1 in modulus is less than or equal to 1 over do that reverse inequality. And since the z's that we're talking about here are on that circle of radius r, the modulus is r. So this is 1 over r to the 6th minus 1 is an upper bound on the function that we're integrating. And then the length of the curve, it's a semicircle, so it's just pi times r. So this is less than or equal to 1 over r to the 6th minus 1 times pi times r. And clearly that goes to 0 as r goes to infinity, because the denominator is a 6th power of r, and in the numerator it's just r to the 1. So that goes to 0 as r goes to infinity. So that shows that integral goes to 0 because it goes to 0 in modulus, then it has to just go to 0 itself. So that tells us that the integral from negative infinity to positive infinity of the original real valued function is just equal to the sum of the residues. And we actually calculated these three residues in a previous example. I forgot the 2 pi I. 2 pi I. So that's 2 pi I. And then the residues, if we go to the previous example, yeah, it was this one. We calculated those residues there, and we got that. And so we'll use that here. So it's negative 1/6 of e to the I pi over 6. Then there was like a plus I. And then there was a minus 1/6 e to the, I guess it works out like this. Anyway, this all works out to be, when you simplify it, 2 pi over 3. And then also, if you did the integral from 0 to infinity, it's just half. So you get pi over 3 for that integral there. So anyway, I hope that you're impressed with that. I kind of am. It's a really cool application of theory to get some practical computation without having to, to do any. I mean, the computation's really simple, actually, when you look at what's going on. Yeah, there's a bit of facts and theory that you need to know, but you didn't have to be some sort of, algebraic whiz to work out, the algebra of it. It was pretty straightforward. Okay, I think I will stop there. Hope you enjoyed the course, and hopefully I'll see you again in another class in the future. Bye now.